great welcome to everybody who has joined. So today's lesson, as you know, is our second lesson in our Term 2 series, and today we're going to be dealing with analytical geometry. So before we begin, just to quickly tell you, I am going to be load shed at 6 p.m., but I've got my backup set up. So I may choose to switch off my video at that point when my power dies. But of course, the lesson will go on. All right, so I'm going to quickly share my screen and we will begin. Like before, I like to have the lesson remain as interactive as possible. So please ensure that you are able to type in the chat box to let me know whether you are following or not. I tend to ask a lot of yes and no questions to keep track of where everybody is at. And more importantly, today, I would like for you to type in some of the answers to the questions that we are going to be dealing with. So as you can see, we have 2 more lessons to go, which deals with calculus after we've covered the analytic geometry bit. So what are we going to be talking about today in this lesson? Okay, right. So in this lesson, we are going to be dealing with concepts regarding coordinate geometry. So analytic geometry, as you are aware, was introduced to you through many concepts that you would have learned regarding straight lines and the Cartesian plane since grade 8. Then when you reached grade 10, it was formally introduced to you under the topic analytic geometry, where you would have learned things such as, let me point out, you would have learned about slope. You would have learned about the distance between 2 points. So I'm just trying to adjust something on my screen so I can write. Perfect. Right, so the distance between 2 points. You would have also learned about the concept of the midpoint of 2 points. You would have learned about specific properties about parallel lines. You would have dealt with perpendicular lines and other types of objects, such as properties of triangles, parallelograms, polygons, etc. So all of those things can be tested under the realm of analytic geometry. Okay, so I see someone did mention they're having some network problems. Okay, so as I said earlier, we are recording this, so if you miss a beat, don't stress. You can always go back to the recording, which will be uploaded onto the NETEX YouTube channel, so no need to stress. All right, so as I was mentioning, those are some of the topics that end up being covered, and then in grade 12, you would have been introduced to the concepts of circles. So you would have looked at the equation of a circle. Okay, so these are some of the things that I plan to essentially touch on today in the lesson. So what I'd like to point out to you first is what you see when you pitch up to write your exam. So when you are writing your exam, you are going to be given a formula sheet. Right, this is what the formula sheet looks like. And what I want to draw your attention to now are the formulas that will be applicable to us under the section of analytic geometry, which is what we are covering today. So of course, we need to understand how to describe the graph of a straight line. So how do we describe it algebraically? And we would be able to do so using y equals to mx plus c. And of course, this point slope method is one of the ways in which you could characterize and describe that linear function, okay? So the m, of course, is the slope, which is given by the change in y over the change in x. So I'm just reminding you about all of these things. And of course, utilizing some of our understanding of trigonometry, we also realize that we can describe or determine the slope of a line, right? The gradient of a line by tan of theta, where theta is the angle between the x-axis and the line in the positive direction. Okay, wonderful. Right, so those are the things that I wanted to bring your attention to. And of course, the equation of a circle, which we will be paying closer attention to during today's lesson. Okay. All right, so let's recap on some fundamental things that we had just observed. So of course, and that is the highlighter. Let's just redo that. Okay, so we know, as we had seen from the formula sheet, that the gradient of a straight line is given by the change in y over the change in x. So if this is what we have, change the color. Perfect. Right, so looking at what we have, here is the y-axis, here is the x-axis, and here is a straight line, which is given by y equals to mx plus c. So just an arbitrary straight line. But of course, by looking at this line, you would be able to tell me whether it has a positive or a negative gradient, or whether the gradient is 0. So what do you think is going to happen with the gradient in this case, based on what I have displayed on this Cartesian plane? Is it positive, negative, or 0? Great, and we see the responses in the chat box are, it's positive. So yes, the gradient in this case is indeed positive. The line is rising. Okay, and what I want to point out here, okay, so that's one way that we characterize it. And then just to go back to the basics, if this was a point given by x1, comma y1, and that was a point given by x2, comma y2, then we know that this formula can be rewritten as y2 minus y1 divided by x2 minus x1, okay? Then some of the other concepts that we had seen and discussed in the formula sheet was the concept of the distance between 2 points. So there are 2 points on this straight line, but let's call this point A and point B, and of course those are the coordinates for it. So the distance between A and B, as you had seen from your formula sheet, is given by the square root of, and if we go back, here was your formula. So you take the 2 coordinates that we had obtained and you write it out in that way. Okay, so I'm just quickly summarizing what it is that we were required to do. All right, so it's the difference between the x coordinates squared being added to the difference between the y coordinates, of course, taken in the same order when we're doing this, squared again. Okay, so we take x2 minus x1, or if you wish to take x1 minus x2, perfectly fine, being added to y2 minus y1, all squared, and then the root of that. So this formula is a metric. What it's doing is it's telling you what is the length of the line segment between point A and point B. That is essentially what this does. Now, what happens if I wanted to know what is the middle point, the halfway point? So if I was going to travel from city A to city B, and I wanted to make a stop halfway through my journey, so I would like to know what would be that coordinate, what would be the coordinates for halfway through my journey. So we then call that the midpoint, which I'm now labeling M, okay? And so the midpoint of AB is nothing but, of course, a coordinate. So that's something to remember. We want a coordinate. So it's of the form x, comma, y. So what does the x coordinate look like? It turns out that you sum the 2 x coordinates, as you would expect, and you divide by 2. And likewise for the y-coordinate. So we sum the y-coordinates and we divide by 2. So that gives me the halfway point. So I just wanted to ensure that everybody understands what the formulas represent. So remember that in summary in here, we've seen that the gradient can be positive, right? That indicates that the line is rising, okay? Meaning that as x increases, so does y. If the gradient is negative, the line falls. So as x increases, y decreases. And we can have that the gradient is 0, which means the line is horizontal. Okay, remember, if the line is vertical, then the gradient is undefined. Can anybody tell me why? I'm just stating some properties in here. Why do you think that the gradient of a vertical line is undefined? So let's just say that was another coordinate and that was another coordinate. Because the line is vertical, it means that the x coordinates must be the same. Isn't that so? So we'll have some y1 coordinate there, but here the x coordinate is the same and a different y coordinate. So I see we've got some answers in the chat box. Right, and we see that division by 0 is not allowed. Perfect. So in the denominator, we would have x minus x. Isn't that so? This would be x. And that would be x, which equals to 0. And we cannot have division by 0. So 0 cannot be in the denominator, making that line undefined. So keep those properties in mind. Those are the different cases that you could encounter when it comes to straight lines and gradients. We do have a question in the Q&A about running this program during the holidays. Yes, I will certainly look into that. We will discuss it and we will send out a poster for holiday lessons. I'm glad that you are all finding this beneficial. Okay, so this was a summary of what the formulas do. Now, before we answer a question from the past papers, the other thing that I would like to point out to you is properties of straight lines. So, some properties. The first property that I want to talk to you about, and I'm sure you already know about it, so let me recap with you, right? So the first one that we want to discuss is, okay, let's talk about parallel. Right, so when are two straight lines parallel? Do we have a criteria to determine if these lines are parallel? So two straight lines, I'm using shorthand, are parallel. So I hope everybody knows what parallel means. Two lines, if they are parallel, then it means that the distance between the two lines, it's equidistant between consecutive points, right? So if we had to draw a line, for example, this line and this line, we would say that it is parallel if the distance between that point, and likewise another line here, it's equidistant, right? So the distance is uniform between the two lines. It simply does not change, okay? Right, so, so that was just the definition of parallel, but now we want to have some type of characterization in terms of the slope of the line. So two straight lines are parallel if and only if, so it goes in both directions, the gradients, right? The gradients of the slope, one and the same thing. The gradients of the two lines are equal. But are we done? Does it take care of all of the cases? Let's look at our chat box. Yes, wonderful. Parallel means they're going to have the same gradient, exactly what we just discussed. But we have looked at a few cases here, right? The line could rise, it could fall, could be horizontal, and it could be vertical. And when it's vertical, look at that, the gradient is undefined. So when the gradient is undefined, it certainly is not considered in this case here. So we could add to this definition to make it a bit more concrete. So we say that two straight lines are parallel if and only if the gradients of the lines are equal, or both gradients are undefined. Because if they're both undefined, it means that they're both, vertical. And if they're both vertical, then, yep, they are parallel based on the definition I gave there. So both gradients are undefined. So keep that in mind. That could have been an easy one to have omitted. Okay. So if we had to draw this picture, okay, I hope I can draw it parallel. Perfect. I think that looks parallel. Oh, that one doesn't. Okay. Let's pretend that it's drawn perfectly. Right, so these lines are parallel. Let's just say that was line 1 and that was line 2. Then the gradient of line 1 will equal to the gradient of line 2. So that was our first case. The other case that I was trying to describe to you was undefined. Okay, and if we're looking at this undefined situation, then this. So clearly, these two lines are vertical. They're perpendicular to the x-axis, right? But they are also parallel. So this is line 1 and this is line 2. Then we see the gradient of line 1 is undefined. Clearly, right? You will see that it is undefined because of the fact that you're going to have denominator equals to 0. And likewise, the gradient of line 2 is undefined. So we can conclude that these lines are parallel. Okay, so keep that in mind. Right, the last thing that I want to quickly talk to you about is perpendicular. Right, so who wants to explain to me what do you mean by perpendicular? Chat box is open to you. When are two lines perpendicular? So two lines are perpendicular if we have an angle of 90 degrees between them, right? Perfect. Thank you for that answer. So now how do I characterize it? How do I describe this using slopes and gradients? That's what we want to know. So two lines are perpendicular. So typically we have the following notation for perpendicular. That's what we write. And for parallel, we do the following. We write that. So if you see that being written, we are referring to parallel. Oh, wonderful. So I see that you have got the characterization typed in the chat box, and that is when the products of the two gradients is -1. Thank you. That's precisely what I was going to write down. So two lines are perpendicular. If and only if, so of course, when we're talking about these lines, we mean straight lines, okay? If and only if the product of their gradients is -1. Okay, so pictorially, if we wanted to describe this, okay, so let's just say I have my lines, line 1 and line 2, there's a 90-degree angle between them, so we know they're perpendicular, then it would turn out that this would imply that the gradient of line 1 multiplied to the gradient of line 2 must equal to -1. Furthermore, if we know that the gradient of line 1 multiplied to the gradient of line 2 equals to -1, then you can conclude that the two lines are perpendicular. So the good thing about what I've written down here is the fact that these statements are if and only if statements. So not only could you work in one direction, but we could use this in both directions. So if you have two parallel lines, you can immediately conclude that the gradients are equal. Or if you know that two gradients are equal, then it means the lines whose gradients were these equal ones must be parallel. And likewise, when understanding or utilizing this result about perpendicular lines. Okay, so now that we've gone through this, let's discuss the following problem. Oops. Okay, so this is question 3 from the November 2020 paper. We are told the following, that ST is given by half x plus 6. Okay. So where is ST? ST is the following line. All right, so that's the line there. So let's quickly jot down that equation. So y equals to half x plus 6. Wonderful. So that's what we have. Okay, good. I'm just checking the Q&A in the chat box. We're all good for now. Okay, right. So that was the first line that we had read. It then says that ST cuts the x-axis at M. Perfect. We see that that's happening there. All right, so we've got that there at M. W is given by the coordinates -4 and 4. So we've got M, we've got that coordinate, and it lies on ST. Is that true? Yes, it is. And R lies on SK. Where's SK? SK is the line segment that's here. Of course, it extends all the way up to N. So that is something that we know. What else do we know? WR is parallel to the y-axis. Okay, so this line segment is parallel to the y-axis. That's good to know. And it cuts the y-axis. So WK, let's see, WK cuts the x-axis at V and the y-axis at P. Yes, that's correct. We see that that is indeed happening. Okay. And KS cuts the x-axis to produce TSK, represented by theta. Wonderful. So we see that there. Okay, so this is our picture, and this is what we are going to be going through. The first question says, calculate the gradient of WP. Where is WP? WP is the line segment from W that cuts at this point P, but of course it continues to K. So if we're calculating the gradient of WP, it's still representing the gradient of WK. But in any case, are we able to easily calculate the gradient of WP? That's the question. Okay, so question, what was that? It was 3.1. Wonderful. We want the gradient of WP. So do we have the coordinates for W and do we have the coordinates for P? Yes, we do. Isn't that so? Okay, someone's already given us the answer. And we were told that the answer is -2. So let's verify quickly calculating on our own if that is indeed the case. Okay, so my load shedding has kicked in. My backup internet is in place, but of course, if something happens and I drop off, you need to wait a few minutes while I reconnect. But I think all should be well, so let's continue. Okay, so we're going to verify what the gradient is. This should be a very easy question to answer. We've got the coordinates -4 and 4 and 0 and -4. -4 and 4 and 0 and -4. We know that the gradient of WP is equal to y2 minus y1 divided by x2 minus x1. So let me use this as my y2 and that as my y1. So that's going to be -4 minus 4 divided by 0 minus -4. This gives me -8 divided by 0 plus 4. So this gives me -2, as was already indicated in the chat box. So this one is a routine question. You just have to plug it into the formula and see what you get out. Okay, let's go back to the question. Show that WP is perpendicular to ST. Okay, so WP was this line segment. We just found the gradient of WP. And we want to show that it is perpendicular to ST. Do we know anything about ST? Yes, we do. What do we know? We know the equation of the line ST. It is given by y equals to half x plus 6. So since we know this, what is the gradient of ST? Gradient of ST. Perfect, right, so everybody says the answer is half, perfect. Right, so we all agree that here the gradient equals half. So I know the gradient of ST and I know the gradient of WP. Don't you think we already have the machinery to check if the two lines are perpendicular? Let's quickly recap on what we had learned. When are two lines perpendicular? They are perpendicular if the product of the gradients is -1. So that's what we're going to do. We're going to quickly verify that. So question 3.2, we have that the gradient of WP is equal to -2, and the gradient, which you had just told me, of the line ST is a half, right? So we need to check, is the product -1? So we see that WP times the gradient of WP times the gradient of ST equals to -2 times +1/2, which is indeed -1. And so since it is -1, we can conclude that these two lines are perpendicular. Hence, ST perpendicular to WP. And so we have answered that bit of the question. Right, the next question says, if the equation of SK, what is SK? Let's look at our diagram. Right, so SK is this bit. Okay, so if the equation of if the equation of SK is given to be this, we need to calculate the coordinates of S, which is here. How should we go about doing this? So, is there anything special about where S belongs or where S lives? Observe that S lives, or S is a point that lies on two of the straight lines, isn't that so? Do we all see that? It lies on the straight line SK as well as the straight line ST. So we have the equation of the line for ST. It is given by half x plus 6. We were just given the equation of the straight line for SK. So all we need to do is equate them and solve for the point of intersection. Does everybody follow my logic and reasoning here? We're solving for a point of intersection. Perfect. Right, so let's proceed to answer this question. Okay, so ST is half x plus 6. Question 3.3. This is the equation of ST. Y equals to a half x plus 6. And then we're also told that the equation of SK, what was that given by? Let's go back. SK 5y plus 2x plus 60. Let's write that down. 5y plus 2x plus 60 equals to 0. So one of the ways that I think you are more used to is taking this linear equation that we have here. It's written in general linear form, what you're seeing here, and writing it down back in the form y equals to mx plus c, because then we would have two equations where the subject of the formula would be y, and then we could obviously make them equal to one another and solve for s. So I'm going to rewrite this equation. Okay, and so we see that this equation tells me that 5y equals to negative 2x minus 60. I hope that you agree with that. And so if I want to make y the subject of the formula, I will divide both sides by 5. So this gives me negative 2 over 5x. And then negative 60 divided by 5, which is negative 12. Okay, wonderful. So I hope everybody's following. And then now what do? Now we take this equation. So I'm going to call that equation 1. This one equation 2. Okay. And what we're going to do is we're going to equate them. So we're going to let equation 1 equal to equation 2, and then we're going to solve. So let's proceed to solve. So we've got minus 2 over 5x minus 12 equals to a half x plus 6, and we solve for x. And once we're done, we'll take that x value, plug it into one of the equations, and we get out the value for y. So let's proceed. So the first thing that maybe would be wise for us to do is to get rid of the fractions, okay? So I typically don't like to work with calculators unless we're forced to using some trigonometric identities. So let's multiply both sides by 10. So if I multiply both sides by 10, then what do I get? Then I get that this becomes negative 4x minus 120 equals to 5x plus 60. Isn't that so? And then we see that then clearly we have a negative 9x equals to, so if I add 120 to both sides, I get 180. And so what does this imply? It implies that x equals to 180 divided by negative 9, which is nothing but negative 20. So did everybody follow that? So the only reason I've multiplied is because I wanted to get rid of the fractions. I've made the equations much easier to work with since we now have these, the coefficients are no longer fractions. Does that make it clear? Okay, wonderful. And we've got a whole bunch of yeses to say that you've all understood. Right, so we've got the x value of s. We now need to find the y value. Of course, what you could do is plug it into any of these equations and we get out the answer. So let's substitute x equals to negative 20 into y equals to 1/2 x plus 6. I think that was the equation. Yes. So we see it's a half multiplied to negative 20 plus 6. So that's negative 10 plus 6, giving me negative 4. So the coordinate then, S is negative 20, comma, negative 4. Does everybody agree with that? Is that what you get when you also do the calculations? Wonderful. We've got some responses here that it's clear. Great. So that was that question. Let's go back. What else did we need to answer? Length of WR. Here's R. Here. Okay. So the length of WR, how do we go about doing that? Any suggestions? So we observe that the point R is lying on the line that is parallel to the y-axis, isn't that so? So what do we do in this case? So we know the coordinate. Do we know the x-coordinate of R? That should be clear, isn't that so? By virtue of the fact that that line is parallel to the y-axis, it means that the x values are fixed, isn't that so? Well, let's go back and check. Right, so if you had to look here, right, so this is the point that we want to deal with, isn't it? So we want to look here. This line, as we were told, is parallel to the y-axis. So that means that the x value here at this point, which is -4, is also the x value here. Wouldn't you agree? This is what I was pointing out. So this must be -4, comma, some y value. I don't know what the y is, but I know that x is -4. Someone wants to just relook at the question. Perfect. The question says, calculate the length of WR. So of course, in order to calculate the length of the line segment, we know we're going to use the distance formula. But before we use the distance formula, we need to find out what is the coordinates of R, right? And we're halfway there because we know that the x coordinate of R is -4, but we don't know what the y coordinate is. Can we calculate that? Yes, wonderful. Someone said substitute the x value of R into the equation of SK because we were told what SK is. So that's good. So let's go back and calculate the y value of R. I'm going to scroll back down to where we were doing the calculations. So this is now question I've forgotten. I think it's 3.4. R is -4, comma y. And we've got the equation of SK. I think we had rewritten it in a different way. Here was the equation of SK, but we rewrote it like that. So it's -2/5x minus 12. Y is equal to -2/5x minus 12. We're now going to substitute in 4. So y equals to -2/5 into -4 minus 12. What do we then get? So this is positive 8/5 minus 12. Okay, and then we see that if we had to simplify this, we could write it down as a proper fraction of -52/5. Okay, so -52/5. So that's the coordinate. So it's -4, comma, -52/5. Everybody happy with this? Okay. And now we're in a position to use that distance formula. So let's do that. So we've got the two coordinates. We want the distance between which two points? Let's go back to our question. We want the distance or the length of WR, which means the distance between the coordinates W and R. So we're going to look at W and R. Okay, so what was the coordinates of W? The coordinates of W was -4 and +4. And then we had just seen that R is -4 and we just calculated it. Where did I write it? Here it is. Right there. -52/5. Okay, and of course, it will be really simple to simply apply in here our distance formula. So what did our distance formula say? So in this case, you're going to need your calculator. It's perfectly fine if you take it out. Okay. I won't use one, so I'm going to rely on you to give me the value. Right, so we know that this is now equal to the square root of x2 minus x1 squared plus y2 minus y1 squared, and we take the root. So I'll write down what you're supposed to plug in. You can then put it into your calculator and give me the answer to 2 decimal places. Okay, so we'll go, okay, so of course we're going to get 0 on this end. -4 minus -4 being added to -52/5 minus 4 squared. Okay, what do you get? I'll just await some responses. Of course, the answer is going to be positive. It's going to be 72/5, it looks like. Is that true? 14.4, yep. Okay, so we're going to use 14.4, I think that's 72. 14.4. Okay, is everybody in agreement that this is the value that you've gotten? Great, thanks everyone. Okay, so we've now calculated that length. I see that we are running out of time and I wanted to talk to you about circles. So let's see how much more of this question we've got. Okay, calculate the size of theta. Okay, this is a nice question. Okay, so this is what I want to draw your attention to. So I won't spend too much time doing this since I want to talk about other stuff. So here is theta. Where does theta actually lie? If we observe, we've got a triangle in here, isn't that so? Isn't theta the exterior angle of triangle NMS? Does everybody agree with this? Right? So theta is the exterior angle of triangle NMS. So what we will aim to do to solve for theta is we will find out what is angle N and what is angle M within the triangle. And then we will add these two things together. So let me call that alpha, and I'll call this one phi. So we will see that theta is going to equal to the sum of those interior opposites there, right? So this is based on the exterior angle of the triangle. So does everybody follow when I say that theta, which is the exterior angle of triangle NMS, will be obtained by taking alpha, that angle, and adding it to phi, that angle there. Is that clear? Great. So if we agree with that, then all we have to do is now solve for alpha and solve for phi. But is that easy or not? What do you think is going to happen? What is alpha equal to? How do I get it? Can I calculate beta? So what do we know? Do you remember this property that we had seen earlier? Right, so the angle between the x-axis and the straight line is going to equal to the gradient. Okay, so we know what the gradient of the straight line is, right? We've got the gradient of sk. What is the gradient of this line sk? Let's go to our calculations. I think we've got it here. The gradient is, that is a poor choice of color, minus 2 over 5. Do we all see that? The gradient of the equation of sk, the gradient for that straight line is minus 2 over 5. Right, so the gradient of sk equals negative 2 over 5. So if I want alpha, essentially what I now need to do is I need to find the reference angle with respect to beta. So let's calculate what is tan inverse. So we're now going to take your calculator out, make sure that it is set to degrees and not radians if you're using your Casio calculator. And what we need to do is we need to find out what is tan inverse of negative, well, we can put into, just put in 2 over 5, that's fine. Okay, so I need you to do that. I can't see. I've got a calculator here, but I've got no light. So I'm going to try. Okay, I've got 21.80 if I round off to 2 decimal places. Do you get the same thing? I'm just quickly checking the chat box. Wonderful, yes. And so the angle here, alpha, is actually going to be given to us. So this is also alpha because of vertically opposite angles, okay? So the angle that we are looking for is 21.8 degrees. So then we want to find what is phi. Do we know anything about the line here with respect to phi? That's the question. Do we know anything? What line is this? This line is ST. Do we know the gradient of ST? Yes, it's equal to half. What is tan inverse of half? So again, if you could just take out your calculator, make sure it's set to degrees, not radians. I need to find out what is tan inverse of half. So again, it's simply utilizing that property. So I'm looking at the chat box, 25.56. Is everybody happy with that? Let me try and shine some light on mine. Tan inverse of half. Yes, I also get 26.56. Perfect. 565, so we can round off to 2 decimal places, so it'll become 26.57. Thanks. Right, so let's do that. 26.57. So remember, we are finding all of these angles by utilizing the fact that we know the gradients of the straight lines. And so we now know what alpha and what phi is. So we sum the 2 angles together and we will get theta. So you take 21.8 and 26.57, add them together, and you would get the answer that we wanted. So if I just moved that out of the way for now. So what is the sum of those two things? 21.8 plus 26.57, and you get a final answer of 48.37. Let's say that, right? I think this is what we all have. Perfect. So that's how we go about calculating it. And then, of course, there was one more question. Okay, so this question says, let L be a point in the third quadrant so that we create parallelogram SWRL. Okay, so let's look at that. So now I'm going to try and erase what we were doing. So here's S, W, right? So that's the W. Here's R, and L is going to be some point here in this. This is the third quadrant, right? We are in the third quadrant here. So somewhere here, possibly. Okay, maybe not there. Maybe here. Say maybe here. Such that when we join these lines, so let me use maybe light green. Right, so such that when I join these, we end up with a parallelogram. What is the property of a parallelogram? So obviously my diagram isn't perfect. So opposite sides have equal length. So SW will have, okay, this is called L, right? Will have the same length as LR. Similarly, SL will have the same length as WR. And the diagonal line, which is SR in here, will bisect the parallelogram, meaning it splits it into two halves. Of course, the two halves are triangles, wouldn't you agree? So what is the question? The question said, calculate the area of this parallelogram SLRW. So I'm not going to solve it because it's already 6:30, but I'm going to tell you what you're going to do. So as I mentioned, the lengths of the sides here. So this side, SL, is the same length. This one is the same length as WR. So if you wanted the length, you could easily calculate the length of this side using the distance formula. And SW, which is this side, has the same length as the other side, LR. Again, you could easily calculate the distance between SW. In fact, I think maybe we did it already. I know we calculated WR. So we already have the length of WR, so that will be useful to you to know the length of this size. So what would we do? I explained that the line in the middle bisects the parallelogram. So you've got two triangles here. That will be equal. In fact, they're going to be congruent. Do you remember the definition of congruent? Congruent means they're identical, they're isomorphic, everything is the same, right? So the lengths of the sides are the same, the area of the two triangles would be the same. So if you can find the triangle, sorry, if you can find the area of this triangle, find the area of triangle SWR, then you simply double it and you will get the area of the entire parallelogram. Does everybody follow the logic and the strategy for answering that bit of the question? So to find the area of the parallelogram, we are going to find the area of triangle SWR because the other triangle has the exact same area. Wonderful. So we have yeses in the chat box again. All right. So that is going to be the strategy and the protocol that you will follow. So I hope that this was helpful. Of course, we had done far less than I intended to do, but I think we needed to spend our time going through that in detail. So what I was not able to cover with you today was the following. I was going to go through the equations of a circle and answer the following question with you. But what we will do is we will post these notes to you so that you still have this question. You can attempt it. And as someone had suggested, perhaps during our lessons that we will host during the holidays, the holiday lessons, we could call it summer school or something like that, then we could review this question that I was unable to answer today. Just a quick reminder before we end that we do have 2 more lessons that are running in which we will be covering calculus. So I will see you again on the 19th of May and the 2nd of June. I thank you for joining and staying with me until 6:30 today. So stay safe, and I'll see you in 2 weeks' time. Thank you.